Hello everyone, welcome back to another video of Math 215. In this video, we shall be discussing how we can derive what is known as the Cauchy-Riemann equations for the Cartesian representation of complex numbers. Where if you're still unfamiliar or if you forgot, reminder, the Cartesian form of complex number is z is equals to x plus iy. Now, to derive the Cauchy-Riemann equations, we must state the following assumption that we've made, and not just assumption, we must have it such so for the Cauchy-Riemann equations to come about. We must have that if you have the function f of z, which is equals to u x y, so separate multivariate function u, which is dependent on x and y, plus I v, again another multivariate function, which is a function of x and y. Now we must have that this function f of z at z naught, which is equals to x naught y naught, basically has the property that it is differentiable. I repeat, we must have that the function f at z naught is differentiable, or yeah, it's differentiable. We shall express f prime z naught in terms of the partial derivatives, and that's how we're going to derive the Cauchy-Riemann equations. First, I'm going to write what we mentioned above, that the fact that the derivative exists, that the fact that it is differentiable, we can write f prime at z naught in the following manner, where we can take the limit where delta z tends to 0 of delta w by delta z. Now this is the definition of taking a derivative of a function which is complex valued, as you saw in the previous week's video on differentiation. Now we can separate out this delta w, since your w, remember this is w, okay? W has a separate real part and a separate imaginary part. So taking a limit operator here, if you were to have a limit, take a limit here, it would hit the real part and the imaginary part separately as well. That's because the limit operator has the linearity property. So we can restate this sort of definition in the following manner. We can write f prime of z naught to be equals to the limit of the real part of delta w over delta z plus I times the imaginary part of delta w over delta z. Now, as I said so before, sorry, there should be a limit here, a limit imaginary part of delta w divided by delta z. As I said so before, the limit operator will hit the real parts and the imaginary parts separately. Now, but we're taking the limits, but we haven't mentioned what we are taking a limit of. So we take the limit of delta x comma delta y, which tends to 0 comma 0. In similar fashion, we have the same thing here. Delta x comma delta y tends to 0 comma 0. Now I'll explain this by using a diagram. So here we have the delta z plane, okay, and there exists a point 0 here at the delta z plane where here the horizontal part is the delta x-axis and the vertical part is the delta y-axis. Now we must have that the that basically our limit of the whatever function we're taking the limit of. In this case, it's the real part of delta w over delta z and the imaginary part of delta w over delta z. We must have it reach z is equal to 0, which is exactly the origin, which is 0, 0. So we must have it such so that in the plane, remember the notion of neighborhood, that our limit must converge to this point using any kind of pathways that it wants. Now, okay, so hopefully you understand this part. So taking a limit where delta z tends to 0, it's the same as taking the limit of delta x comma delta y to 0, 0 here and here. So moving on. Remember the following, I talked about this following statement when we did derivatives, but I'm going to repeat it again. It is important to note the following. The above expression is valid for however we approach the delta x comma delta y tends to 0, 0. Since we had, I'll draw it again, we can approach this point from multiple different pathways, right? But the above expression, as in the derivative, is basically valid for in any way, however way you choose the path. So let me fix a path. Let me try and fix a path and let's see what happens. Let's first approach delta x comma delta y tends to 0, 0, this thing. Let's try and approach it horizontally first and then vertically later, and then see what happens. So if we try and approach, remember this is delta x, this is delta y. If we try and approach 0, as in z is z0 or 0, 0, if we try and approach horizontally, we have this certain trajectory, as in here we're approaching 0, 0 from the x-axis, or sorry, delta x-axis. So the coordinates is delta x, 0. What you're successfully doing here is fixing a value for delta y, which is going to make our life a little bit easier. And it's one of the tricks of complex analysis, and something that you should well understand and be equipped with. And in similar fashion, we can approach this 0, 0 from exactly vertical, from the vertical axis. Here we're fixing delta x, so we fix delta x to be 0, and we have delta y. Since on the vertical axis delta x, or the horizontal component, is 0. So first we fix delta y, or in other terms, we approach 0, 0 horizontally. If we approach horizontally, we approach delta x, 0 towards 0, 0. So having the limit approach 0, 0 horizontally, our f, the first derivative of f at z0, simply changes to this, where we have the limit where delta x tends to 0 for the real part of delta w by delta z plus the imaginary part taking the limit of the imaginary part of delta w by delta z. Now, if we further break it down, I'm gonna erase this part. Let's further break it down. Let's further break it down. We have f prime at z naught. So the limit of the real part of delta w we have. Now I'm gonna skip a lot of the algebra here, but if you are keen enough, you can look at the lecture notes for Math 215, which I have uploaded in the Google Drive and have posted the link on Slack. And if you're not on Slack, please join Slack as soon as possible. A lot of people are already on Slack, and I talk about a lot of things on Slack as well. It's very important and it's necessary that you join Slack. Now, I've skipped a lot of steps, but what happens at the end is the following algebra, the following statement, sorry, where we have the limit delta x tends to 0, and we have u by u, which is a function of x naught plus delta x, comma y naught minus u x naught y naught. Now, it's very easy to note that this is something that you have seen in the derivatives video in week 2, plus also our limit operator. It's the imaginary part. We have delta x tends to 0, v x naught plus delta x y naught minus v x naught comma y naught divided by delta x. Since we're approaching delta z tends to 0 from the horizontal. So if we further break it down, this is simply by definition would give us du over dx at x naught comma y naught plus I dv over dx at x naught comma y naught. Now, if the jump from this step to this step seems confusing to you, please watch the derivatives video again. If this is by definition, taking the limits of these functions would in fact give you these partial derivatives. You did it, we saw for normal derivatives, but it's the same case for partial derivatives. Okay, so I'm gonna write the partial derivative form in another sort of format where we have I simply denote the first partial derivative of u as u subscript x at x naught y naught. So whenever you see a u subscript x, now you must, for complex analysis, you should try and always attribute this to being the first derivative of the function u with respect to whatever the subscript has. Okay, and here it's x, so it's with respect to x, plus I v x x naught comma y naught. So here we have, if we take the derivative of f prime z naught and we approach it through the horizontal line. So let's try and see how our derivative would look like. Just remember, f prime of z naught is the same no matter how you approach it. So let's see how it would look like if you were to approach it vertically. So if it were vertical, we would have f prime at z naught. As we did it for the horizontal case, I'm not going to repeat the algebra, it's a simple algebra. So we have f prime at z naught. I'm just going to go to a similar step like this one. We have f prime at z naught. If we were to approach the limit vertically, the limit delta y tends to 0, and we have in similar fashion u, which is a function of x naught comma y naught plus delta y minus u of x naught comma y naught divided by I delta w. Since remember, you're approaching it from the vertical the vertical is what? The vertical is the imaginary axis. So you have I delta W here if you approach it from the vertical, which is why you had an I delta W. Sorry, delta Y. Sorry. If you were to approach it through the vertical, you would get I delta Y. If you want, I can show it again. We have delta Z is equals to delta X plus I delta Y. So if you were to approach it from the vertical, your delta Z simply is I delta Y, since our horizontal part is 0. So getting back to this is our first statement. Now we get to our vertical part, taking the limit of the vertical part, taking the limit of the imaginary part, sorry. So we have the limit where delta Y tends to 0, I in front of the limit, V x naught comma y naught plus delta W delta Y minus V x naught comma y naught divided by, again, I delta Y. And remember, oh, here you can cut the I here and the I here, and remember always this following identity, that 1 over I is simply minus I. Okay, so if the inverse of I is simply minus I. So invoking this identity here, okay, we can take this I upstairs, which would give us the following breakdown, where we have the limit delta Y tends to 0. As you can see, what was the imaginary part has become the real part, and what was the real part has now become the imaginary part. So rearranging it so that the real part is in front of the imaginary part, we have V x naught comma y naught plus delta Y minus V at x naught comma y naught divided by delta Y minus, taking the limits, I times, since I can take it out of the limit operator, as it does not depend on delta Y, limit of delta Y tends to 0 of U x naught comma y naught plus delta Y plus delta Y comma minus U of x naught comma y naught divided by delta Y, which is basically, if you were to write it in this format, would break down like the following. We have f prime at z naught is equals to Vy, subscript y as in the first derivative with respect to y, minus, since there's a minus here, minus I times u y. There you go. Now you have two separate evaluations of f prime. One where you take the take the approach or the pathway of calculating the limit from the horizontal, and here if you were to calculate the limit from the vertical, since taking the derivative of f at z naught is similar irregardless of whatever path you have taken, we must have that this is equal to this. So if both of these statements are equal, we will have, let me erase this part. I'll write all of it again. We have, if we were to go approach from the horizontal, you would have ux plus I Vx. I'm not going to write the x naught y naught as I've written so before, since it's sort of implied, since we're taking the derivative at the point z naught. And also, you also have if you were to approach it from the vertical, f prime at z naught is equals to vy minus I u y. Okay, so both of these statements are equal to each other. So we can further write it like this. Ux plus I Vx is equals to Vy minus I U y. Now, remember that in both sides, the real parts must equal each other and the imaginary parts must also equal each other. So since the real parts of f prime from left hand side and the right hand side must equal each other, and in similar fashion the imaginary parts of the left hand side and the right hand side must equal each other, we have the following two equations. The first equation, for the real part, we have ux is equals to vy, since these are the real parts for the respective left hand side and right hand side. And for the imaginary part, which would be the other equation, is simply, for the left hand side the imaginary part is vx, and the right hand side the imaginary part is minus uy. And there you go. These are what are called the Cauchy-Riemann equations. Now, is this derivation necessary for you to memorize or to do it yourself? It's to memorize, basically? No, it's not necessary for you to memorize. But I would suggest doing it because deriving the Cauchy-Riemann equations gives an insight as to what derivatives actually mean and how to and the concept of approaching limits. As since approaching limit, but how you approach the limit doesn't really matter. So thank you and hope to see you again in the next video.